We are going to look at delta G calculations, and this would be page 15 of homework packet 17. So what you can see here is part of the AP exam equation guide. And let's see. So I got this Q, remember heat equals CM triangle T mass. We have specific heat or heat capacity, change in temperature. So remember when we were doing thermodynamics way back in quarter one, we had this equation. We might see how we're going to combine that back together. Now, I think what might have looked familiar was delta H sub naught. You could either get that through Hess's law, or you could take heats of formation of products minus heats of formation of the reactants to figure out your delta H. So a lot of times you could either use Hess's law or heat of formation tables. Well, notice when we're looking at Gibbs free energy, we can do the same thing. Delta G of the products minus delta G of the reactants. And we can do the same thing with entropy, except instead of talking in terms of delta, we actually just talk in absolute terms, because with entropy, we actually get a grounding point what zero entropy is. That's a crystal solid in its natural state. So everything we have, we know an entropy for that, so we don't even have to put the deltas in there. But it does work the same way in that it's products minus the sum of the products minus sum of reactants. Okay, and there are just some of the different terms that we have here. Notice what's going on. We have this formula delta G equals delta H minus T for temperature, delta S. I think we've talked about that. Notice how we're going to be able to link delta G to the equilibrium constant. So I think we talked about if something's in equilibrium, delta G is 0 and K equals 1, but we can really find that at any value, whether K is way greater than 1 or way less than 1. And then in the next unit, we're going to link this to electrochemical cells, and we're going to see what E sub naught is cell potential and how that works, standard reduction potentials or cell potentials. So that's a little roadmap for where we're going and what we're going to do in this problem. And here we go. So just a thing to note, delta S is measured in joules per mole K. Delta H and delta G are typically in kilojoules per mole. So if you get big numbers by your delta S, remember this is in joules instead of kilojoules. And so it's really going to be 1,000 times less. Now notice as the equation works, there's going to be a K value here for Kelvin that this one doesn't have, and we'll see how that works in. One other thing to note, in the standard state, delta G and delta H, we said heats of formation are 0 for elements in their standard state. But unless something's a solid crystal at 0 degrees, it does have an entropy, so that doesn't imply when we're working with our entropy values right there. Okay, so let's go to the next thing. And we have a table, and it says that the value of the standard entropy change delta S for the reaction is negative 232 joules per mole Kelvin. Calculate the standard molar entropy of C2H6 gas. All right, so there's a few things going on here. And I think one thing I'm going to bring to attention is that we have this formula for this equation. I'm going to say delta S of the sum naught of this reaction is going to equal the products delta S of C2H6 minus this reactant C2H2 minus 2 times this reactant, which is delta S sub naught of H2. It's a little bit small there, but that's what we're trying to do. Now notice we're actually given what delta S is for the overall reaction. So that's negative 232.7. Okay, and it is in joules per mole Kelvin. I'm not going to put that in right now, but we don't know what this is right here. So this is kind of a mystery. It has a value, but we're going to try to solve for that. We do know this is 200.9 right here, and we do know the H2 is 130.7, but we have to multiply that by 2 because of the coefficient. So I have negative 200, and then I'm going to flip this over here. It's going to be it's going to be like negative 232, and then I'm going to get another positive here, or negative 32, and then we get another positive here. Um, so it's actually quite a positive value. Now, would we expect any entropy value is going to be positive? So we better get a positive number here. And notice the units are joules per mole Kelvin. So I knew everything was joules per mole Kelvin, so I didn't keep those units there, but I just put it on at the end. So that is our first example of solving for this value right here, knowing the final, knowing the other two components, but not knowing that original component there. Okay, let's go to question B. Calculate the value of standard free energy delta G for the reaction. What does delta G indicate about this reaction? Well, I don't see anything about delta G here, but I know there's an equation that links delta G and delta H and delta S. So I think I got a bunch of stuff about delta H. So I think I got to solve delta H. I know delta S for the reaction, and then I'm going to have to work to find delta G for the reaction. So how do I find delta H for the reaction? I do take the products minus the reactants. So the products were C2H6 was the product, and then C2H2 and 2H2 are the reactants. So this time I'm trying to find delta H for the reaction, and I know all the components. So I kind of looking at this equation, instead of thinking of it in terms of delta S, I'm thinking in terms of delta H. So I took the negative 84 minus the 226.7, and then minus 2, well, times 0, which is 0 because heat of formation of an element in its normal state is going to be 0. So anyway, I get these numbers, and I get negative 311.14 kilojoules per mole. All right, so I'm just thinking about in thermodynamic favorability. Um, this is, yes, this is thermodynamically favorable if you're trying to form products, which is leading me to think, oh yeah, delta G will be negative, but this is not thermodynamically favorable. Notice I'm not looking at the one I found in my question mark. I'm looking at the delta S of the reaction because it's getting um, less entropy. We're moving toward less entropy here. So how does that all add in together? I'm going to take my delta G sub naught equals delta H sub naught minus T delta S sub naught. And we're assuming, I think we're at 25 degrees Celsius, which is the standard state conditions we do these in, which would be 298 Kelvin. And I'm going to say delta G equals negative 311, and that's kilojoules per mole. And then I say minus 298 times 232.7 joules per mole K. Okay, and notice, so I multiply by the temperature, and then it's joules per mole K, and I get something like 69,000 some, but that's joules, so I kind of did this and went back to kilojoules. Notice a negative and negative makes a positive. So we're talking in terms of delta G. That's, oh, this was very thermodynamically favorable to our products. This is not thermodynamically favorable. Still, when I combine the two together, it still is a pretty big delta G value, negative 242.1 kilojoules per mole. And we could say that's spontaneous. Now AP likes us using the words thermodynamically favorable for forming those products. So what would the K value for that be? The K value for that is going to be delta G sub naught equals negative RT ln of K. And I just took that off of that AP equation guide that I have. And I solve for ln of K, delta G sub naught over RT. Notice what R I use. There are a bunch of values there, but use the 8.315 joules per mole K. And then notice I took this number, but I converted to joules because this is in joules. So I got negative 242,000 instead of just negative 242. Okay, notice you divide by the 98 and I get 97.8. Well, that's the natural log of this. So if I take the inverse natural log of this number, I get 2.98 times 10 to the 42nd, which is a really big number, which means it favors products by an extreme amount. So it's virtually going to completion at this temperature. So the question is, if it's favorable at some temperature, not at other temperatures, there must be a crossover temperature. If I keep raising the temperature, it's going to make this delta S term become more and more important. So at some point, I'm going to reach a temperature where it's actually delta G is going to be equal to 0. Okay, so it's not going to favor reactants or products. And then I'm going to cross over where it favors the reactants. What is that temperature? Pretty easy. I'm going to sub this in and say, T equals, or T times delta S equals delta G over delta H, negative P over delta S. And then what I do is just solve for T, and I end up with T equals delta H over delta S sub naught, and that way I can solve for delta G, okay? And, or if I set delta G equals to 0, that's why I can do that. So I set delta G equals to 0, and then I just do the algebra to get for this temperature. And then what I do is I'm plugging in this value for delta G up here. I'm plugging in the delta S value of negative 232, which we had here. And then what I'm going to do is I get joules per mole over joules per mole K, and I end up with 1,338 Kelvin. So, I mean, that's a high temperature, but if you're like if you're like trying to melt a metal or something, that's about what it is. It's not extremely high, like millions of degrees, like in, side of a star or something like that. So notice at this temperature, this isn't favorable in the forward direction anymore. It's actually at equilibrium. Anything greater than this, it favors the reactants. Anything less than this, it favors the uh, it favors the products when you do this particular reaction right here. All right, hope that helps. See how this can be looked at quantitatively. Thank you.